Okay, good morning, everybody, and thank you for the nice introduction. So indeed, during this talk, I'm going to present the results of our research concerning a novel physics-informed neural network approach, which is meant to deal with the reconstruction of multimodal vibrations and their inversion using a set of sensor data, which are normally sparse, um, in order to identify unknown elastic properties that we are seeking for a specific part. It's a research outcome of my collaboration with my colleagues at Ghent University in Belgium, and also here with IMO's lab, APFL. During this talk, I'm going to first have an introduction to the research institute that I'm coming from. What are the motivations behind this research? And then we will see how a physics-informed neural network can handle a vibrational case study, and what are the challenges and how we tackle those challenges by the proposed methodology. And finally, the results and concluding remarks. So I'm coming from Flanders. It's a research institute in Belgium, in the Flanders region. And the aim of our research institute is to help with the digital transformation of manufacturing industry specifically. We have three core research lines. One is on end-to-end design of products. The other more focuses on the products with motion elements. And one core research line focus on production and assembly itself. And we think those that core lab on motions, we in the sensing and monitoring tech domain, we are dealing with the problem of using multimodal sensor data in order to do condition monitoring, in-process monitoring of manufacturing and end-of-life evaluation and remanufacturing. For all those, we have to do the diagnosis, prognosis, and control tasks using sensor data that are typically sparse. Sometimes we don't have access to all components of a or all spatial domain of our component. And sometimes it's also, we are dealing with weakly known physics in the problems. So that's the idea behind development of physics-aware machine learning technology. And one of the very informative and valuable sources of information that we receive from the sensors is the vibrational signal. And typically what we do in order to have a vibrational evaluation of our test piece is that we inject vibrations, or we use the inherently available vibrations of a test piece. And because of the multimodal, multi-scale nature of the vibrations, they have they interact differently with the component and its internal structure. And the same way they provide us with multi-scale information about the component. It could be some global information, material properties, and thickness. It could be some localized information about presence of damage somewhere in the component. In any case, we need to measure the vibrational response. You have two choices. One choice, as shown on the left side, is to have a sparse measurement data. On the other side, we could have costly equipment like a laser Doppler vibrometer to have a full field vibrational measurement of the test piece. So we have two extremes. One extreme is a sparse data, more reliance on physics of the problem and a statistical analysis. On the other side of the extreme, we have a lot of data. It needs costly equipment. It's quite time consuming. And of course, we don't have always the accessibility to everywhere on this sample to do the measurement. So we are going willing to go more towards the left side to have less data, or somewhere in between using undersampled data. There are a few alternatives to do that: model-based inversion, compressed sensing, or like black box regression using neural networks. But we are more interested in physics-informed neural networks because they have proven performance in seamlessly integrating data and physics together for this purpose. If we use a black box regression using neural networks for the vibrational problem, what we do is that we train a neural network, we embed the coordinates as the input, and we have the vibrational response in the output. We have a data-driven loss term to be minimized for the mapping. And in order to make it physics-informed, there are different ways to do that. But here, what we mean by physics-informed is to enforce the governing equations of the problem at a set of collocation points. We calculate a physics-driven loss. We have a total loss to be minimized in such a way that we enforce physics everywhere. And if there are some missing aspects of physics or physical properties, we can at the same time infer them. So our approach to the vibrational problem within the context of this study is like shown here. So we have a set of sparse locations for sensing the vibrations. We use the time signals to identify modal frequencies, and then we use those modal frequencies for two purposes. First, to reconstruct mode shapes, full field corresponding to those modal frequencies, and on the other hand, to identify unknown elastic properties of the test piece. We can ultimately go for time domain reconstruction and damage localization, which is beyond the scope of this talk. This is the case study that we consider. It's about vibrations of composite laminate. It's a carbon fiber composite laminate with cross-pole layout, meaning that the fibers are oriented in 0 and 90 degree every other ply. And then the composite laminate is fixed at the 4 corners. We also consider possibility of releasing one of the corners bottom right so that we have different configurations of the boundary conditions. And the governing equation is the classic laminate theory. It's a single degree of freedom force order equation, and we have 4 elastic coefficients to be identified for the problem. So in order to examine physics from neural network, we generate virtual data. For that, we do the finite element simulation. We add noise to the data. We calculate mode shapes, add noise to that, and we use a set of measurement points as virtual test data, and we couple it to the governing equations imposed at a set of collocation points. So to start with, if we train a neural network, physics-informed neural network, we have the coordinates x and y as the input. In the output, we have the bending deflection as the single degree of freedom of the vibration. We additionally do backpropagation throughout the network. We calculate the spatial derivatives because we need them for the physics-informed loss. And then we have the total loss. And in order to simplify the elastic stiffness identification for the moment, what we do is that we consider an overall stiffness scaling, which proportionally scales over stiffness parameters. We start with an initial guess of 0.5, and we need to converge to the correct value of 1. Anyway, there are 2 challenges. One challenge is that our governing equation is a fourth order one. The elastic terms are defined by high order terms. The inertial terms are defined by low order terms, and it's not easy to regulate those high order terms. And if the elastic stiffness is not known and is going to be inferred from the neural network, it trivially converges to 0 in order to make this equation happen. And in order to tackle this problem, what we did is that we reparameterize our equation into a second order equation by introducing additional output variables as the second spatial derivatives as shown downside. And at the end, we have additional loss terms to make sure those converge to the correct value. Another challenge, which is maybe the main focus of the study, is the spectral bias of neural networks. We would like to reconstruct vibrations that are multi-scale. The complexity increases as the frequency increases. So we have to reconstruct those vibrational patterns. And on the other hand, neural networks tend to converge to the less complex, or let's say low frequency modes of vibration. We consider sign activation function in order to induce periodicity, and also we consider locally adaptive activation functions to induce some spatial periodicity, higher spatial frequency, to possibly improve this spectral bias. So let's see how such a physics-informed neural network can reconstruct a single mode shape. It's not a high-frequency mode shape, it's a low-frequency mode shape. And we see that if we consider a uniform set of measurement points, as shown on the image with black circles, none of the cases with different scalings of the activation function can manage to reconstruct the mode shape. And as expected, the stiffness identified is always converging to a lower value, meaning that it's trying to, in some way, apply the physics by minimizing the stiffness, and it's not successful. So far, none of the measures helped with it. And so that's why we thought it's better to do the reconstruction in another space, in a spectral space. And it's actually triggered by the fact that we know the vibrations are sparse in the wave number domain, or K space. If we test it for a single mode shape and we convert it to K space by using two-dimensional Fourier transform, we see that we have two real or cosine maps and imaginary sine maps. They are very sparse, and on the other hand, we see that they are complex. They have complex conjugate property diagonally, so only half of the space is sufficient. So it's sparse, and it also includes the multiscale behavior of the vibrations because of its spectral definition. So what we do is, instead of reconstructing vibration itself, we learn the coefficients associated with the spectral components. We consider a set of Fourier basis functions that are cosines, as shown on the left side, and sines as shown on the right-hand side. And they are symmetric and antisymmetric when we use a centralized spatial domain. The good thing about it is that, first of all, we transfer the complexity into these basis functions. And on the other hand, as shown on the bottom, when you have the coefficients, you can also calculate spatial derivatives of any order without requiring backpropagation throughout your neural network. So that's how we build the K-space physical informed neural network. We receive, rather than receiving coordinates, we receive a vector of modal frequencies. We map them into a set of coefficient images, real and imaginary components. And we do spectral superposition to calculate the bending deflection and also its spatial derivatives. And we additionally consider a sparsity promoting loss terms to make sure that the K-space is sparse. Then one question is that, okay, how wide should we consider this K-space? How wide band should it be? Of course, the wider it is, the reconstruction is going to be more accurate, but then it's going to introduce so many spectral components that makes the neural network confused. In order to help with this, we consider an adaptive Gaussian mask. We apply it as a prior low-pass filter to our K-space, and then we let the neural network learn whether it should enlarge the bandwidth or narrow down the bandwidth for every single mode shape. So that's the full pipeline of what we consider for the K-space PINNs. So we receive measurement data, we calculate the modal frequencies, we feed them to neural network, we have real and imaginary coefficients of the K-space, we apply an adaptive mask, and by superposition of the spectral components, we have the vibrational response and derivatives to calculate the loss terms. Okay, let's see how it works if we, instead of using a single mode shape, reconstruct 10 mode shapes up to 1 kilohertz, including different scales, symmetric modes and antisymmetric modes. This is the results of 3 selected modes. chosen from the low frequency to high frequency regime. And you see that at the different columns, we have different distribution of data provided to the physics-informed neural network. A uniform grid, the same number of data points, but randomly distributed, and a sparse number of sensor data randomly distributed. And in all cases, it successfully managed to reconstruct the mode shapes fulfilled. Here you see the results of reconstruction error for all 10 modes and also the identified elastic coefficient. And I should emphasize that here we use a lot of data, 2,400 data. So whatever we get from finite element simulation as the sensor data. So you see that all modes converge quite instantly together. There is no big difference in their convergence rate. And also elastic stiffness is converging to the correct value of 1. If we don't apply the Gaussian mask, the reconstruction error is a bit lower, but the stiffness factor is wrongly identified. It means that it's more it's more data-driven training than physics-driven training, highlighting why would we need the Gaussian mask. This is with a lot of data. We are not going to use it like that. If we use limited data points, here is randomly distributed points of 96. If we use the Gaussian mask the same way, just like having a lot of data, it converges very good in terms of reconstruction error and identification of elastic coefficient. But if we don't apply the Gaussian mask, neither the identification of stiffness nor the reconstruction is successful. So especially if we have limited data, it's very important to apply that kind of Gaussian mask. It's not only about having symmetric or antisymmetric modes. If you release the bottom right corner of the plate, we have asymmetric modes, and the same way those symmetric and antisymmetric spectral components reconstruct our mode shape. And so far it was based on considering an overall stiffness scaling factor. We can the same way use it for identification of individual stiffness factors. We start with different initial guess values and we converge to the correct value of 1. It's a bit more tricky because when we have individual stiffness factors, we have to make sure that the mode shapes that we choose, they are wisely chosen for maximized sensitivity to those, but still by having a randomly or arbitrarily chosen set of 10 mode shapes, we have a good estimation of those individual stiffness factors. And finally, in terms of computational efficiency, we see that it's much more efficient if we compare them in terms of the neural network size, as shown on the left-hand side. So if we increase the width of neural network, the computational cost of a standard physics-informed neural network increases a lot, while the while of k-space is staying the same. And the main reason behind it is that we don't need to do additional backpropagations to calculate the spatial derivatives while they are done by the spectral definition. And on the other side, we see the effect of the number of collocation points is constantly lower than the normal or standard physics-informed neural network. And the reason behind it is that we don't use, again, the neural network to calculate every single spatial point. Instead, we do it afterwise as a post-processing by a spectral superposition. And even further, so far, we are not using the power of fast Fourier transform. If we have a uniform grid of data, by the assumption of that, we can use fast Fourier transform, and the computational cost is going to be much lower. So to conclude, we can say that we can use the k-space in order to have reconstruction of vibrations or any other solution that could have this kind of sparsity in order to have good reconstruction of multimodal responses and identification of unknowns. And the good thing about it is that apart from multimodal reconstruction, it is explainable because it's providing us about what are the wave numbers and the spatial frequencies that are present in our response. And also it can inform us about the symmetry or asymmetry of the response. And finally, because of the spectral definition and derivation of the derivatives, it can save a lot of computational cost for us. If you're interested to know more details about it, I would like to invite you to have a look to our full paper in that regard. And of course, I would be happy to discuss it further later on. Thank you.